So this is the extra thing you get by having complicated motions. If there was just ballistic motion, there will be zero, there will be no diffusion. But as you're jostling around, this is very good pedigree. The version that we tend to use is due to Einstein 1905 paper. And it's not very much appreciated, but the reason why this young man could do general relativities as well is that these are very closely related subjects. So being an exquisite statistical mechanician was a natural staging for the other things we know. This is a beautiful paper, and what he says is that if I look at x squared for isotropic system, so x squared, so I have a molecule and I'm finding out where it is, or I have a bunch of molecules started at different initial conditions in a state space. So it's a trace of this object, where isotopy, in the sense that left is equally likely as the right, tells you that the average of this is zero. Then the main thing you can compute is the variance, and Einstein says that there is a number, so limit of t goes to infinity of 1 over t is proportional to some constant, so that's called diffusion constant, and is already he lived in 1, 2, 3, 4 dimensions. It was very natural to define it in such a way that per each dimension you get diffusion. So if you're on a line, you can hope, right? But if you're on a plane, you have this and that. You want to add up these things, and they will add up because of this rule. So there'll be average diffusion per direction, and because you can go left and right, he put the number 2 here. So that's the diffusion constant. And this quantity is just definition of diffusion constant. It doesn't tell you what causes the diffusion. So you could imagine that it's jostling by the molecules. If there is no isotropy in your dynamics, for example, if you're on a square or cubic lattice and there's difference between going along it as going to 45 degrees to it, you will actually be measuring a tensor. So there could be a diffusion tensor. I'm looking at Jeffrey because he just got a prize. So that looks hard, but then we have this amazing formula that says, well, I don't have to worry about this. I just compute this function and take its two derivatives. They don't know it, but they have diffusion in all the systems they're looking at. And we haven't measured it. There's a graduate student in Germany who has done it for a pipe flow, but we haven't done it for any of the interesting cases that we care about. And we can do it. It's totally within reach, and we have to do it. It's, once you understand it. So this would be an amazing prediction of theory of chaos if we knew how to compute this derivative. It turns out we do, and it's extremely simple. So in the lecture that 3 people attended in this room, I explain how. So there are things called cycle expansions.